Industry uses steel, which comes in a variety of shapes and sizes. This closed-die hot press is forging crankshafts for the motor industry. Each piece of steel has been cut from a bar, and those steel bars began life as scrap. You can't just take this scrap metal, melt it down, and turn it into steel bars. Industry demands bars of a certain shape and dimension and a specific metallurgical composition. To achieve all that, you have to subject the steel to very precise and expensive processing. The process is known as rolling. By rolling steel, you can produce rods, bars, plate, and sheet. At its simplest, rolling is the squeezing of steel between pairs of specially shaped solid rotating cylinders. They're called rolls. Rolling calls for steel with good malleability, and the hotter the metal, the more malleable it is. First of all, the scrap has to be melted down. That's done in an electric arc furnace. At this stage, certain additives can be mixed with the metal to improve its properties. From the melting furnace, the liquid steel is taken to be poured or teamed into molds. Each mold holds 6 tons of steel. When the metal is cool enough, the mold can be removed, leaving a solid hot ingot behind. These are taken straight away to the rolling mill. When they get there, they won't be hot enough to be rolled immediately. First of all, they have to be heated to an even temperature of 1300 degrees centigrade from the surface of the ingot right through to the core. The ingots are heated in what's called a soaking pit. Depending on the quality of the steel and the size of the ingot, they may remain in the pit for up to 8 hours. The pits provide a useful buffer period for the ingots during their journey from the furnaces to the rolling mills. What's wanted is a steady supply of steel at the correct rolling temperature. It can waste both time and money if the whole rolling mill has to stand around waiting for ingots to reach the right temperature. During heating, the ingot acquires a surface scale. When this flakes off in handling and rolling, it carries with it some of the defects which could mar the surface of the ingot. The interior of the ingot has an uneven structure. When it's poured, the hot liquid metal touches the cold surface of the mold. The sudden cooling effect creates small crystals at the surface of the ingot. As you move towards the center of the ingot, this cooling effect is not so marked, and the formation of the nuclei of each crystal is retarded, and the crystals get much larger. So, in a really large ingot, the crystal size can vary a great deal from the surface to the core of the metal. Rolling has a twofold purpose. It gives the steel its desired shape, but it also imparts a homogeneous quality to the metal, improving its tensile strength and toughness. When it's cast, the ingot has a coarse, crystalline structure. The squeezing of the rolls elongates the crystals and aligns them in the direction of the rolling. But since the metal is hot, fine equiaxed crystals are formed at the grain boundaries due to recrystallization. Under the great heat, these grow into larger crystals. As the ingot is passed through the rolls, the crystal size becomes more uniform. As a result of rolling, the crystal structure of the steel becomes more reliable and more predictable.